Yeah. So we welcome you all for the 5 days short-term training program on Big Data and Institute of Science and Technology, Vadapalli, in technical collaboration with NVIDIA. So yesterday we had an introduction to big data and big data technologies, and also we had a hands-on session using Python on NumPy, Pandas, and sklearn. So today our session will be on linear, multilinear regression and hands-on session using Python on machine learning algorithm. So which is conducted by Dr. Shri Vallabha Devi, lead data scientist at Tiger Analytics, and also we'll be having a special session on AI skill enabling. And afternoon also we'll be having a session on pre-processing in machine learning. That's our hands-on. So now I would like to introduce our resource person, Sir Shri Vallabha. Sir is a lead data scientist with Tiger Analytics, and as a part of his role, he leads teams solving business problems in various industries like retail, transportation, and manufacturing, on developing deep learning models for video analytics sector. His current projects are focused on recommendation systems, natural language processing, and prior to this, he was working as a postdoctoral fellow at IIT Madras in statistical analysis of liquid sprays. His doctoral thesis was on large eddy simulation of sprays, a branch of computational fluid dynamics, and his areas of expertise are machine learning, statistical analysis, reduced order modeling, and simulation of physical systems and scientific computing. Sir holds a BTech in Mechanical Engineering from IIT Madras and a PhD in Aerospace Engineering from Indian Institute of Science, Bangalore. We are very happy to have you, sir, and we welcome you for the STTP. Now I hand over the session to you, sir.
Thank you very much, madam. I hope you can hear me clearly, all of you.
Yes, sir.
Okay, I'll start sharing again then. Yeah. So good morning, everybody, and thank you for the opportunity to give a talk on linear regression. Please feel free to stop me and ask in case you have any questions anywhere. That is not a problem. So I would be more than happy to answer questions as and when they come. We can also take them at the end of the session. We'll look at the basics briefly and then go to the hands-on part, because we need to understand a few things before we go to build any model. So this will be the brief outline. I'll talk about modeling in general in terms of machine learning. Then we'll go to regression, and after regression, we will look at what are the things that we need to take care of when we go to build any regression model. So basically, machine learning or whatever we are working on today, all of it depends upon data. If there is no data, there is no machine learning. So machine learning would require data to learn. Broadly, there are two types of data. One is called a structured data set. The other is unstructured data. We will see what the difference between these two is. So structured data is the data that is organized into tables, meaning the data that sits in any SQL database or that sits in any Excel sheet is structured data. So each column has a specific type. The column may be name, roll number, or some ID number or something of that sort. Each row is one observation. One row is one person. Let us say you are thinking of the students in your college. Each row is one student name, and each column will represent something about the student. His or her name, his or her roll number, his or her first semester marks, second semester marks, and so on. Now the data is stored in a database with keys and relations. So there are relations between different tables. If there are multiple Excel sheets or multiple tables, there will be some relation between all these tables, usually called as the key. And all traditional software will capture data in this form. So whenever you think of traditional software like Excel sheets or databases that companies have, they capture data in a relational database, which is mostly a structured data set. And unstructured data is the other type. It is basically the text that you see in documents, website comments, and online posts. So most common example of these are, like say, posts on Facebook, posts on Twitter, or posts on some social media websites where people go and talk about movies or products or anything in general. Then a second category of unstructured data set is the call center voice recordings. People call a customer care center when they have a problem with some particular product. Then what do? They record the call and they can use it for learning. So we can also mine or understand data from them in a structured manner using some advanced tools like deep learning. Then the third set of unstructured data is the camera images from cameras, the photos that you take. Today, Google will tell you, Google is able to recognize faces in your Google Photos. It will tell you whether that is you or somebody else. And the last one is videos from CCTV footages. So basically, these are the two broad categories. Data stored in tables where each column has a definite type of structured data, and unstructured data is everything else, written, spoken, or visual information. Then coming to machine learning algorithms. Now we saw about the distinction of two types of data and what are the types of algorithms that are there. So typically the algorithms that are there fall into two categories. The first class is supervised learning and the second class is unsupervised learning. So supervised learning, the examples of supervised learning approaches are regression, classification and clustering, reinforcement learning. We will talk of regression in this session, but there are two other things like classification also you can do to say whether a item is yes or no. Unsupervised is clustering and anomaly detection. In this case, we don't have any labels to the data, meaning the data is not labeled good or bad or anything. We have to just draw information. So this is more like clustering students in a college or clustering customers in a supermarket. People who come regularly, people who don't come regularly, people who do well in academics, people who need some nudge or who need some push. These kinds of things, there are no labels attached. We only can do clustering and identify different segments of students. And what is the difference between labeled data and unlabeled data? Labeled data is where the data has labels. So if you see in the first column on the left side, there are images, there are also labels of dog or cat. So when there is an image and a label, it is very easy to cast this as a classification problem. Show me an image, I will tell you whether it is dog or cat. That is one class of problems with labeled data. A second class of problems with labeled data is where you have numbers. So there is a dog and there is a weight, there is a dog, there is a weight, cats and their weights are there. Show me the image, I will predict the weight of the cat or the dog. That is the second class of labels that you can see on the data. And regression problems typically fall in this data. The last one is unlabeled data. There is no label attached. You need to draw inferences or you need to be able to group and say the top two are dogs and the bottom two are cats. That is unlabeled data. Now what do? When we have labeled data, we choose supervised learning approaches. Otherwise, we have to resort to unsupervised learning to draw any inference. So this is very briefly about data and the machine learning algorithms. So what is machine learning? Machine learning is modeling on structured data. It is also called as analytics. People say machine learning, people say data science, people say data analytics. All these are more or less referring to the same thing. I don't really see any difference between these terms. There is not much of difference or distinction. The machine learning will have multiple things that it can do. The first class of things are what we saw earlier. Regression, where we predict a continuous value, and classification, where we predict a yes or no flag. These are the two things that we can do on data. We can also group observations, which is clustering, and we can also find anomalies, which are basically outliers in the data set. These are some things which do not belong to this data, that is anomaly. So this can be applied to a variety of situations. Machine learning is not restricted to one or two or specific use cases. You can take it to anywhere you want. And then for companies that have good databases, where companies are collecting data from by using computerized records. If you go to any supermarket today, they'll give you a bill that comes out of a computer. As and when they print the bill, the data is also stored in their SQL database. So for companies that have good databases, this is basically a very good tool. Machine learning is a very good tool to extract insights. We need not worry too much. We can get easy insights or quick insights from this data set. So this is about machine learning. Now coming to regression. Regression is what we are going to look at now. So what is regression? Well, let us start from there. Just a moment. Yeah. So what is regression? Basically, regression is this. You are given a set of values x1, y1, x2, y2, and so on. So it is simply like this. In a very simple context, you can think of regression as the price of a Uber cab based on distance. I need to go 5 kilometers, they will charge say 80 rupees. I need to go 25 kilometers, the charge will be say 350. So x1, y1 are, x1 is the independent variable, the distance I need to travel, and y1 is the fare that might be charged. That is a very simple example for understanding regression. So given values x1, y1, all these are numerical values. We need to predict a continuous value y based on x. So if you tell me 10 trips that you took with Uber, we can try to estimate how much will Uber charge you for a particular distance. That is a very simple example of regression. So what we are doing when we are trying to build a regression model, We are simply trying to build a relation of this form. Y is equal to A plus Bx. This is called curve fitting in engineering. If you go to traditional engineering, mechanical, electrical, they say this is curve fitting. They do experiments, they get scattered data, and they'll draw a least square fit line, which will describe the data. This is the same for spring experiment where you say y is equal to kx. This is also true for voltage and current and resistance. V is equal to IR, Ohm's law. So these kinds of things are all known in engineering as curve fitting or least square fit. Now, in the case of machine learning, we usually stick to straight lines. We don't want higher order polynomials. We will try to fit a simple straight line which will say y is equal to A plus Bx. Meaning, for Uber, for a particular distance, there is a fixed cost and there is a variable cost. The fixed cost is say 50 rupees, and per kilometer they will charge you 8 rupees. If you know that, then any distance you can find out the price of the Uber cab. And how do we construct or how do we fit the straight line? To fit the straight line, we will use what is called as a least square fit. What is least square fit? We will see shortly. All this is very basic understanding. You may not really need to use them in your daily when you are building models, but it is helpful for us to know what is going in the background before we go on to build a model. Now, what is the least square fit? So, given that you have n observations, x1, x2, x2, x1, y1, x2, y2, x3, y3, so on, we want to fit a best fit line. A y predicted, y hat is equal to a plus bxi. Yi is the true value, yi hat is the predicted value. I want to fit a line which will give me a predicted y value, y hat, for a given input value x, where a and b are the fit coefficients. This is what we are trying to find out. We are trying to find out the values of a and b. And if you find out suitable values of a and b, you make an error in prediction. You are never right, or you can never get the answer to be right always. So if the true value is yi, your predicted value is y hat I, there is an error in the prediction. If the true Uber bill for say 24 kilometers was 380 and you predict 360, the difference is an error in prediction. So there is always an error in linear regression when you build a model. The prediction error is this, y minus y hat. And what we want to do, we want to minimize the error for all the observations. There are n observations. For each of those observations, we want to have a minimal error. That is what we are trying to do. So to do that, we go to what is called as a cost function. Cost function is simply the difference between the true value and the predicted value over each observation. You square that difference. So y true value minus predicted value square, and then you sum up over all the observations. So this is the total error that you are making when you build a regression model. And then when do I have the best regression model? We have the best regression model when this cost function s is minimized. And why am I squaring? Why do we need to square? Why can't we simply have absolute, or why can't we simply have the true value as y minus y hat? If you did not take the sign, errors will get balanced out. Positive errors, negative errors will sum up to 0. So taking simply sigma of y minus y hat is not apt or not suitable. You can do an absolute value, but the absolute value can take you anywhere. It will lead to flat surfaces. When you square, what you are seeing on the right side as a surface, it is like a blanket with load in the middle, right? So this is called a convex surface. It does not have any peaks in the middle. There is one local global minima which is only at one point. Everywhere else the value is higher than the global minima. So when you square your residue, when I am doing yi minus a plus bxi, what I am doing is we are making the function to be a convex function. And if you make it to be a convex function, you will get a good estimate of a and b, which is why we are squaring. So the cost function is something like this. And how do we go and fit the least squares, or how do we go and fit the parameters? I will just go through quickly. Don't need to worry too much about fitting, because say models sklearn or Python would take care of it. So when at the lowest, when we have the least cost, when we have the just a moment, I see some drawing here. I'll reshare. If you stop share and reshare, it comes back. Yeah. So when we have a function like this, how do I find optimal a and optimal b? The a and b for which the s will be minimum, or they follow this kind of relation. The partial derivative of s with a and s with b are 0. So when you do dou s by dou a is 0, dou s by dou b is 0, you will get to relations of this form. If you say dou s by dou a is 0, a is simply equal to mean of y minus b into mean of x. Y bar and x bar are mean values. Mean y and mean x. And when you do dou s by dou b is 0 for the other coefficient b, you get a relation of this form: xi into y minus yi, y minus y mean, and xi into x minus x mean. So yi minus y mean is the variance from the mean value, or the deviation from the mean value. Xi minus x is the deviation of x from the mean value. So this is what happens in the background. We need not write equations and solve for this, but this is what happens when you call sklearn linear model and when you do a fit. It is trying to find out A and B such that they satisfy these conditions. A is equal to mean y minus b into mean of x, and b is equal to x into y minus y mean by x into x minus x mean, summed over all the observations. This is what happens in the background when we do a least square fit. Now, if you look at it in the terms of in a graph, this is how it will look. The blue dots are the points. Y2 is the true value. Y2 cap is the predicted value. And the error you are making by prediction is Y2 minus Y2 cap or hat. Y2 minus Y2 hat is the error you are making. You take each error, you square it up and add. So this is one error, this is second error, this is third error, and so on. You try to fit a line in such a way that the sum of squares of the errors is minimized. So the line must be in such a way that the sum of the squares of the errors must be minimal. This is the minimum error that I will see, which is why it is also called as the least square fit. So this is what happens in the background whenever you are building a linear regression model. This is what is happening in the background. It is trying to find out two parameters A and B such that you fit a minimal sum of squares like. Now, what are the types of regression models? We saw one example so far. So the first one is a linear regression. It will only take one dependent variable or one feature and try to predict one output variable. Y is equal to A plus Bx. Now, if there are multiple things involved, if there are 2-3 features involved, if you come back to our Uber cab example, x1 is the distance, x2 can be the time of the day, because all of us know that the prices during peak hours, early morning 8:30 to 11 o'clock and evening 5 o'clock to 8 o'clock, there are peak hours. So there is an effect of the peak time. The same distance at 1 p.m. in the afternoon and the same distance at 8:30 a.m. in the morning are not same prices. So if you bring in the time factor, that will be another variable. So x1 is the distance variable. There is another variable called time factor, and the third one can be something else. Like say you are going to the railway station or you are going to the airport or the bus station. So cabs going back to airport, cabs going back to railway station will typically have slightly lesser fares, because it will help the cab to go there and then be there available for lot of for other passengers. So that can be another factor like that. So when there are multiple features which will decide our output variable y, what is the cost of the cab, distance, time of the day, where am I going to? When these multiple things have an effect on the output variable, we have to build what is called as a multiple linear regression, where you have multiple parameters that will affect the outcome variable, which is the price in our case. Then there is another thing which is basically called as non-linear regression. Non-linear regression is the curve fit that we are talking of. Any questions? I heard some sound. Sorry.
No questions, Dr. Vallabha. You can continue.
Okay, sure, ma'am. Yeah. So the other one is the non-linear regression, where you need to fit higher order polynomials. Now, please pay attention to the two equations. The second equation is x1 square and x1 cube. It is not x2, x3, but the outcome variable is affected by x1 square, also affected by x1 cube, higher powers of x. This is called as a non-linear regression. So if you look at them graphically, a simple linear model will fit a data of the form y is equal to a plus b1x, whereas a polynomial model will fit y is equal to a plus b1x plus b2 x1 square. In most business world, we don't really see polynomial models. Most of the time, what we see are simple linear models. There can be polynomial behavior, but we try to explain them from simple linear models, because that is what is easy for the business to grasp, understand, and take some action on. So that is why most of the time regression means linear regression and not polynomial regression. Then there is another other dimension to linear regression. When there are a lot of features are also called as independent variables, also called as IDVs. They can also be called as features. So these are all the features which will affect the outcome variable, which is the DV. DV is dependent variable. IDV is independent variable. These are all different terms given to values in a regression. Now let us say you are trying to predict sales in a supermarket. Okay, there is a supermarket. whose business owner is trying to predict the sales of items. Now you know that sales of one item may be affected by sales of other items. If it is like say wheat flour and oil or bread and jam, you know very well that if there are high bread sales, likely that there are high jam sales. Now, if the owner wants to know what all items are affecting the sales of one particular item, we have to build a regression model. But do we build a regression model with all the other items in the retail store? That is a question. If there is sales of bread that we need to predict, do we only include jam, or do we also include instant coffee powder, tea powder, or milk packets? Because people may also dip the bread in milk or tea and coffee, right? So when there are a lot of items to be predicted, or when there are a lot of features that will affect or likely to affect the outcome of a dependent variable, we will go into some problems. Okay, what are those problems? We will see. So if you do a simple normal regression, you try to fit the sales of bread as a function of the sales of jam, sales of milk, sales of coffee powder, sales of wheat flour, and sales of oil, you will have too many x values. Your equation y will become y is equal to b1 x1, b2 x2. It will become b100 x100, b500 x500, and so on. You will have a lot of variables. And a normal regression will try to fit everything. Normal regression would not complain. It will try to get some coefficient for each of these values. But the problem with such an approach is that it is prone to overfitting. It will lead to bad predictions. If you try to fit the sales of bread with all unrelated items, you will get some answer, but that is a bad answer because you cannot make a reasonable prediction in the future using that. So we cannot really throw 1,000 variables to fit one single value. So we have to make some reasonable assumptions or make sure that things are fine. So that is where what is called as regularization will come into picture. So what is regularization? We will see. So far what we have seen is, if you have a multiple linear regression, yi is the true value that we know, and a plus b1 x1 xi1 b2 xi2 b3 xi3 is the predicted value, and yi minus this is the prediction error, and the square is sum of the squares. So the cost function is yi minus this. There is a small typo, sorry for that. The 2 is outside this bracket. So we are doing yi minus predicted y, the square of that, and doing a sum. This is the regular cost function. In this approach, we do not have any constraints or any limits on b1, b2, and so on. So what do we do? If I don't want to fit it with all 1,000 variables that are there in the supermarket, we go to something called as lasso and ridge. Lasso and ridge will penalize the coefficients bi, b1, b2, b3. There is some penalty on them so that the model does not overfit. By overfit, we mean to say that the model fits very well on the training data. Model is able to predict very well on the training data. It is not able to predict well on the test data. That is called as an overfitting problem. We will see that also as we go forward. But lasso and ridge are two approaches to do that. How do they do? Lasso applies a penalty on the coefficient. So if bk is a coefficient, there is a penalty. The cost function, the new cost function will include the world cost function and also a lambda times sum of absolute coefficients. So the coefficients cannot really be a big value. It will tend to go to 0. If there is no effect of that particular item on the sales of bread, the coefficient of that item will go to 0. That is what lasso will try to do. Ridge will try to apply a penalty on the square of coefficient. Instead of bk, ridge will apply a penalty on bk square. So s is s0 plus lambda into sum of bk square, where the bk is the coefficient. Ridge is a small variation of lasso. Penalty is on the square and not on the absolute value. Then there is something called as elastic net, which will combine both lasso and ridge. So elastic net is s0 plus lambda 1 into penalty of bk and lambda 2 into penalty of bk square. These are all three variations to linear regression models that we see, which we use when we have lot of variables to be fit into the model. To discard variables which do not make sense, we choose lasso or ridge or elastic net. And what are the lambdas? The lambda that you see here, lambda 1, lambda 2, these are called as hyperparameters, and you set them manually. You don't ask the model to find out. You set some value of lambda so that you get a good answer on the testing set. What is testing set? What is training set? That also we will go through quickly. And then there is another thing called as constraint lasso or ridge. It will apply constraints on coefficients. You want the coefficients to be either positive or negative. You also have an option to do that. That is called as constraint lasso or constraint ridge. So this is useful when you want to find out cannibalization of one product by another product. If other product sales go up, this product sales must go down. So this is, in such case, you should have a negative coefficient. So you use a constrained lasso or ridge. So this is about regularization models or regularized linear regression, lasso ridge. And then classification. Why am I talking of classification here? Classification in the simplest sense is a logical extension to regression. We will see what it is, and then we will go back to regression model building. So classification given x1 and class 1, x2 and class 2, x3 and class C2. So x1, C1, x2, C2 are observations. x1, x2, x3 are the independent values, and C1, C2, C1 and C2 are the classes. So there are two classes, C1 and C2. There are multiple observations, x1, x2, x3, so on. The classification problem is to predict C given an x value. If I'm given an x value, predict the C value. That is what classification is simply doing. Now, how do we do this classification? Classification is simply a restatement or a small function on the top of linear regression. So we fit y is equal to a plus bx. Forget the two in between. Y is equal to a plus bx is what we are still fitting. And once we fit y is equal to a plus bx, we write a probability p is equal to 1 by 1 plus e minus y, e to the power minus y. So 1 by 1 plus e to the power minus y is called as the sigmoid function. So you know a y value, you predict a p value using the sigmoid function. So basically classification is simply sigmoid on the linear regression output. Linear regression output is y, which is a plus bx. You do a sigmoid on that, you get a probability p, and you apply a threshold and say whether the probability is greater than this value, it belongs to class 2. If it is less than the threshold, it will belong to class 1. That is what you are doing when you do simple logistic regression. So there is a linear probability model that you build and convert the linear probability model into p value, which is the curved line. P value is basically the linear line that you see, y equal to a plus bx. When you apply the sigmoid function, it becomes this curve. You apply a suitable threshold and say anything above the threshold is one class, anything below the threshold is a other class. So logistic regression is a simple extension to linear regression. That is why I brought the slide here. Now we will quickly move on to what are the what do you call care, or what is the caution that you need to exercise when you go to build a linear regression model. You simply take the data, do a linear regression fit, and then give an answer. That answer may not hold in the future. When you try to predict on unknown or unseen data, the answer may not hold. Because the answer may not hold, you cannot simply throw one line, you can't do a linear regression and go on and do. You have to take care, which is what we will see. So before you go to do any linear regression model or any modeling assets, we need to make sure of some few things. The first one is data duplicates. Most of the time or some of the times you may observe duplicate entries. What is a duplicate entry? The two rows are identical. There are x1, x2, x3 and y1, y. All these values are same in the two rows, which are basically exact duplicates. So you have to drop the duplicates. There is no use of keeping duplicate data in your modeling data set. You need to drop duplicates. This is the first care that we need to take. The second care that we need to take is to treat outliers. There will be some values in between which will have a lot of which will have a very high value for y. You are trying to predict some y. Some observations will have very large values of y. They are very, very far away from the rest of the data. Now, if you bring them into your model, if you bring them into your linear regression model, the model will be very bad because outliers will affect your data. You need to treat them. You need to throw them away or put them aside. So you need to remove outliers. Then there might be noise in the data. For the same x value, you may see multiple y values, which is basically noise. So noise is something that nobody can handle. You have to either denoise, meaning you have to bring down, for a given x value, I choose one y value, or for a given x value, I choose an average y value. That is what we need to do. Because noise would mean that for the given x value, there are multiple y's possible. What is the true y? We cannot really conclude. So we have to treat for noise also. We have to remove the noise in the data. For a given x, there can only be one y value. These are the three cleaning steps that we need to do before we go on to treat or model any data set for linear regression or for any model for that matter. Then once you do all that, we need to do something else. There are some missing values. So if you have a lot of features, there are 10 features which will predict an output variable. Some of those features may be missing for some observation. So there is a 100th observation in which the 5th feature is missing. What do I do? Do I throw it away or do I do something else? So there are various approaches to treat the missing values. Yeah, I see a raised hand. Purushothaman sir, you can ask sir.
Good morning, sir. I'm Purushothaman. So I have a question with respect to data cleaning.
Yeah.
Sir, like in industry, how do you identify these outliers? Because the data set would be very huge. When we work on toy projects, we actually do try box plot, we search for the quantile range, and that's how we find outliers, if any. But when it comes to a very big, very huge data set, how is it handled, sir?
Yeah. In a huge data set, it will also come with a lot of features, sir. It will not be one variable depending on another variable. You will also have a lot of features, meaning lot of different dimensions which will describe the data. So the techniques that we do there are similar to what you said. We will do quantiling, we will do Z scores and all, and then based on that we will do an outlier removal. The only advantage in industry is you can do outlier removal using multiple features. So let us think of Uber cabs, sir. Most of the time the cabs are during the day. If I see a cab at 2:45 a.m. early in the morning, that is the only observation I see. I can usually discard that because that is an outlier in terms of time. So similarly, if I see a Uber cab in Chennai that is booked for a distance of 5,000 kilometers, the distance is an outlier, I will discard. So you will have different features to do the same process, that scores or quantiles, but you have different features. So you have multiple ways to cut the data set. That is what is usually done. If the outliers are indetectable, we go to anomaly detection techniques. Sir. We try anomaly detection and things like that to find out probable anomalies and keep them away from the data.
Okay,
I
sir.
hope
Thank
that
you,
answers. Yeah. So, any other questions here? Okay. Then we will go to the next part. So there are missing values. If you have 10 columns which will describe the output variable, all the observations may not have data for all the 10 columns. People make multiple choices. Sometimes if you have a lot of data, you will have the luxury of discarding all the rows or all the observations that have any missing value. If I have say 10, if I have 10,000 entries with 10 features, 10 x1, y, x1, x2, x3 up to x10 are the features, y is the predicted variable, and I have 10,000 observations, I have no problem. I can actually throw away all the missing values and the data set may become 6,000 or 5,000. That is still okay for me. But if you have very few observations, I have only 500 observations and I need to predict, or I have 1,000 observations and I need to predict the coefficients for 10 features, then you may not have the luxury of throwing away. You have to do something. You have to do mean imputation or median imputation or model based imputation. There are a lot of things that we need to do. I'm not covering them here just in the interest of time, but missing value treatment itself is a big topic. Then the second one is the dimensionality reduction. So the data set may have dimensions. So the data set may have multiple dimensions, which when you reorient the data set, when you transform the data, would become unidimensional. So if you see in this case, F1 and F2 are two dimensions on the data set, and the data set seems to have significant variation in F1 as well as F2. But if you transform them and move them into a new coordinate system E1 and E2, you see that most of the variation is only along E1, and on the E2 direction there is not much of a variation. If it is like this, you can build a model only based on E1, you need not worry about E2. So this is called as dimensionality reduction. When you have 25 features, you want to reduce it into a smaller set, we do dimensionality reduction. Then the last one is scaling. What is scaling? In scaling, different features in the data set have different number ranges. So again, coming back to our Uber example, if you think of time in seconds for the trip and the distance of the trip in kilometers, the distance of the trip in kilometers would be like 25 kilometers, 30 kilometers, 50 or at most 100. But if you do time in seconds, the time will be in the order of thousands or 10,000. So if you simply do, if you build both of these into the regression model, because they have different ranges of numbers, you will get a bad regression model. So you have to scale them. By scaling, we mean a variable which is very large number is scaled by the maximum number into a range of 0 to 1. Similarly, a variable that is smaller also is scaled into a range of 0 to 1. So ideal regression model, all the features would be between 0 to 1 range. And how do we scale itself is a different, is also, there are a lot of things that people do when they scale. They simply scale by the maximum value, they shift to the mean, and then they scale, so that you do observation minus mean value by max minus min. That is a kind of scaling that we do. So whatever scaling we do, we make sure that all the features in the regression data set have similar ranges. The minimum value and the maximum value of different features is more or less similar. If it is similar, the coefficients will be better and your regression model fit will be good. So this is the third thing that we need to do when you go to build a regression model. Even before building a regression model, we need to do these kinds of studies. Then once we go to model, this is the overfit model that I was referring to. So there is an x value and there is a y value. If you for a moment imagine x value is our Uber distance of the ride, and y value is the cost of the ride, say in tens of rupees, 50, 60, so on, whatever you can call it up to be. Now, if I simply draw lines between observations, this is my model. If I say, I know these two data points, I will draw a straight line fitting them. I know these two data points, I will draw a straight line fitting them. If I do something like this, on any new data point in between, the model will give very, very bad answer. The model answer should be very bad. Now, if I know all this, tell me what is that, what will be the cost for a trip of 10.5 kilometers. So this is 10, say this is 11, 10.5, what is the trip value? That would be a very bad estimate in reality. So this is an example of a overfit model. We should not build a model like this. We cannot do something like this and get off. So we have to build a true model. Now, how do I make sure I build a good model? So that is when we come to what is called as the training and testing split. So if I had 100 observations, let us say the data set has 100 observations, I would not build the model on all the 100. I will take 80 observations randomly, build a model on the 80, and then predict on the remaining 20. When I say predict on the remaining 20, I am holding out 20 x and y values. I am predicting 20 y values based on the 20 x values, and then estimating what is the error in the model. So then I will know whether my model fit has been good or bad. So this is how we need to test out a model when you build a linear regression. If you want to go to even more rigorous approach, I want to do hyperparameter tuning. I have a lambda in my model. What is the best value of lambda? If I want to know that, what do we do? In that case, we fit the training data. We split the training data into multiple training sets. So you see the partitions are multiple training sets. So let us say we split our training model into 10 splits or 10 sets. Then if I want to train a hyperparameter, I will train within the training data itself. I made it into 10 pieces. I train on 9 pieces, predict on the 10th piece. Then I train on another 9 pieces, predict on the 10th piece. So we do this repeatedly. This is called as n-fold cross validation. N-fold is the number of divisions you do in that training data. And once you optimize your hyperparameter based on the n-fold cross validation, you go to the testing set. Now, there is another approach that people use. If you have even bigger data set, you have the luxury of large data with no problems at all, you can even do training, validation, and testing. Meaning, I will do training, I will test on the validation set. If the error comes out to be minimal, then I go and see the value on the testing data set. Now, just one thing to remember, all this data we have with us. When we go to build a model, we have training data, validation data, testing data with us. We are choosing to not see these two pieces while I am training. After training, let me look at validation. If this is fine, I will validate multiple models on the validation data set, pick the best model, and then go and look at the testing performance. So this is what people do when you have a lot of data. All these are depending upon the data set that you have, but the most basic step or essential step is to do training and testing. Without a test data, there is no model. You build your model on the entire data and say my model is very good. Your model may fall flat tomorrow when we put it in production, when you make a prediction. Then what are the different types of fits that we see? By fit, we mean how good is the model in terms of explaining the data. So a very bad model or underfitted model is here. There is variation in the data, but the model, the blue line, is not able to explain it clearly. So this is what is called as a underfitted model or a poorly trained model. Now, if I use lot of features, whatever is there, I will throw in and try to build a model. It will look to be something on the right side. This is called as an overfitting model. The model will fit very well on the training data. Whatever data you know, whatever data the model knows, it will fit very, very well. You will see that the test metrics are very, very good. You will say this model is excellent, but the moment you take it to reality, again it will fail. So we have to avoid underfitting models. We also have to avoid overfitting models. The trade-off is somewhere in between. The model does reasonably well both on seen data and unseen data. So a good model is simply the one that will do reasonably well, not best. It will do reasonably well on training data and also reasonably well on the test data. If I am predicting errors, the error prediction on the training and error prediction on the testing are reasonable or comparable. The training error is 1%, testing error is 50%, very bad. Training error is 50%, test error is 2%, is also bad. Training error 5, test error 7 is reasonable. Both of them are comparable. So when we try to build a model, we need to focus on something here. Then what do we do about model evaluation? All this is fine. We have built a model. What are the metrics to evaluate the model? Did you get a good model? Did you get a bad model? How do we know? So model evaluation is given by these things. These are called as, there are some metrics. The first metric is R square. R square is also called as coefficient of determination. It will measure how well the model is able to predict the observation. So the formula is this. I will show it graphically very soon, but it is simply 1 minus sum of squares of the regression model by the total sum of squares. Total sum of squares are yi minus the mean value. If I predict the mean value of all the y's and give it out as a prediction, there is an error I make. So take that mean value minus yi and do sum of squares. That is the total error. This is the worst error that you can make when you build a model. And then regression is, you build a regression model, you predict the y hat. What is the error between yi minus y hat? This is what the R square will do. So very simply put, when you are talking of R square, the question is this. The red line that you are seeing here is the mean y value. I saw y values from y is equal to 0 to y is equal to 35. I sum up all these and do a mean value. The mean value is around 14. So for any observation, if I give a mean value as an answer, how much bad am I doing? That is the mean value, or that is the base model. On the top of the base model, we will try to improve. That is what we are trying to do. So the total sum of squares, the denominator that we saw here, the denominator that we saw is SS total, which is this, is basically this. I give a mean value, the error is this, square of this error, and so on, and do a sum of squares. That is the SS total. That is the maximum error that you will get if you give a mean value as the output. Now, if I fit any linear regression model, the errors will reduce. So there is a model that I am fitting. This is the error now for observation 0. This is the error for observation 2. And there seems to be no error for observation 1. So there are new squares of errors. This is what we see in the numerator, SS regression. So these squares by these squares is the ratio that we are making, that we are improving. 1 minus that is the R square. And an ideal R square, by this we understand that an ideal R square will be close to 1 because the sum of squares of regression will be close to 0. So you have to hit as high R squares as possible. Now, going by the expression that we saw earlier, you might not really see a negative R square, but if you do a very, very bad model, the data looks like this, my model looks like this, your R square value can be negative. Even though it is sum of squares, it can be negative because the model fit is very, very bad. So your model should never get a negative R square. Model must have non-negative R square. It can be 0, it can be 1. 0 R square is very bad, 1 R square is a good model. You will try to fit a model which has as high R square as possible. Then there is a small nuance to the R square. If I keep adding features, I build a model with 1 feature, 2 features, 20 features, 30 features, R square will keep increasing. It will never decrease. But then the true increase, is it coming because the model has become better, or is it because the features have increased? So there is a new other metric called adjusted R square, which is given by this formula. Adjusted R square is this, n minus 1 by n minus p minus 1, where n is number of observations and p is the number of features. So adjusted R square is a true indicator of model improvement. The improvement is not coming from simply adding features. Improvement is coming because the model has become better. This is what adjusted R square is. Now MAP is another metric where you measure the model accuracy. It is simply y minus predicted y by y, which is percentage error, and you do 100 by n, mean of absolute of percentage of error. Error is y minus yi, percentage is by yi into 100, and by n is the mean value. So this is a MAP value. People typically use MAPs when you are trying to predict non-zero numbers. But if the number is 0, if the yi value is 0, MAP will go to infinity. If yi is 0, the error, even if you make a small error, your percentage is infinity. So MAP will lead to abnormal values. In such cases, we use what is called as a mean absolute error. Mean absolute error is simply y minus yi has absolute value by n. This is another metric where your prediction, if the predictions have 0 in them, you use MAE instead of MAP. And another metric is RMS error. Root mean square error is another metric that we use. So you can use any of them based on business sense. People stick to MAP if it is non-zero values. If it is 0 values, they go to MAE. If you want to look at some other signals, they may also choose to use RMS. And finally, coming to how good the model is, please think of it like this. Think of it like a player throwing darts at a dart board. The board that you see is a dart board. The player is throwing n darts, say 10 darts, and these darts are hitting somewhere. You look at the lower corner, you see that the player is consistently hitting in a region. He is hitting somewhere, he or she is hitting in a specific region. There is not much of spread, but that is off from the bullseye. If the bullseye is in the center, the true predictions are drifting from the bullseye. They are away from the bullseye. So this is called as a bias. Bias is a error from the true value. Consistent error from the true value is bias. There is a drift, but there is also low variance. Variance is how spread are your observations. Are my predictions all over the place or are they close? So the variance is small because you are hitting consistently in the same place, but because this hitting point is different from the mean value, there is a bias. So this is one kind of an error. Another kind of an error is there is a bias. The darts are on the mean, the darts are hitting away from the bullseye, and they're also spread all over the place. This is called as a high bias, high variance model. The model is neither good in terms of bias, meaning it is not hitting near the center, and it is not also hitting close. They are hitting everywhere. So this is a worst model. This is a model somewhat better than the other model, but you don't know whether you are correct or not because you don't know what the reality is. Then there is a third kind of model, which is they are close to the bullseye only. This player is sitting near the bullseye only, but they are spread all over the place. It is spread. Sometimes he hits up, sometimes he hits down. This is a high variance and a low bias model. And the last one is a model that is ideal, which has low variance, meaning the spread of the darts is small. There is not much of a spread, and it also has a low bias. All of them hit near the bullseye. So we need to build a model like this. Now, how do I understand that? Do I need to throw darts to understand my model? No. The only thing you need to understand is what you are plotting here as errors. The dots are the errors that you are making, and the bullseye is the zero value. If your errors are spread all over the place, you have high variance in the model. Your errors are not spread so much, but they are consistently away. Your model has a bias. So that is what the right side plot is telling us. The red line is the bias error. As you fit the model, a poorly fitted model will have high bias. So there is a high error in the training data. This is the training error. The red line is the training error. The blue line is the testing error. So when the model is very bad, what you have is high training error. As you improve the model, as you train the model further and further, what happens is the training error will keep reducing. It will look very nice to you that if you train the model for 1,000 iterations, 10,000 iterations, the training error will keep on reducing. It might be a good thing for you to see. But there is another thing that we need to notice. What is the test error? The test error will initially be low usually, and then as the model complexity increases, as you are overfitting the model, the test error will start to shoot up. Shoot up meaning it will start to increase. So training error will be very low and test error will be very high for a high variance model. So the model will hit all over the place. So you need to look at the total error, which is the absolute sum of training error and test error, and go to and stop at a place where the training and test error together are minimal. So that is where you have an optimal model. It is not a overfitted model. It is not a underfitted model as well. So this brings me to the end of the talk, and thank you, and let me know if you have any questions, and then we can move on to the hands-on session if everything is fine here. Any questions so far on the model building or on things like this?
No query as such, Dr. Vallabha, so we can proceed to the hands-on session.
Yeah, sure. So we'll move on to the hands-on session. I have shared a data set and a folder with you. Ma'am has shared the link with all of you. You may be able to access this. We will talk of this. So the data set for this came from here. If you are familiar with Kaggle, in Kaggle there is something called as New York City Airbnb open data. So this is basically the description of the data. Airbnb is a aggregator of hotel rooms or rooms for travelers. So hosts are people like you and me who have spare rooms in their house, which they can lease out or rent out on a daily basis to visitors. And the visitors can go to Airbnb and make a booking on Airbnb. So what do we have here? We have different things about the rooms, the type of the room, the location of the room, what are the facilities that are available in the room, whether you have AC or whether you don't have AC. These kinds of stuff are all listed out. And these rooms have a what do you call target price. The host would lend out this room only at a certain price. So this data set is about Airbnb listings. Listing meaning the properties that people have listed on Airbnb to be rented out and the probable prices for them. For prices meaning what is their ask price? How much do I want? The host will say, you don't really say, you give me something. If you are putting a room or Airbnb, you will give a number. You will say, I would want say 500 rupees per night or 2,500 rupees per night, depending upon various factors. So all the data is shared. This data is available to you for free. You can go and download the data just by registering yourself with Kaggle. What I have done is downloaded the data, put it here, and then I'm trying to do some modeling on this. We can do the modeling on Kaggle. We can also do it locally. Yesterday there was a Kaggle crash, a Gmail crash, and Collab did not work for me. So I also have a local copy with me. The same data is in a local folder. If this one doesn't work, we will go there. I hope all of you are familiar with Kaggle. Is there anybody who is not at all familiar with Kaggle or new to Kaggle? Just please raise hands so that I will only do an introduction of how to get into Kaggle. Sorry, Google Colab. Very sorry. I hope all of you are familiar with Google Colab. If anybody is not familiar, please raise hand. I will not ask you any questions. I'll just show you how to go to Google Colab or how to start a Google Colab file. Okay, then I'm assuming all of you are familiar. Even if you're not familiar, it is simple. Go to your Google Drive. It can be your personal Gmail account as well. Go to your Google Drive in your personal Gmail account. You click on New. It will show Google Docs, Google Sheets, Google Slides, Google Forms, and so on. If you click on More, it will show other apps, which are Drawings, My Maps, Sites, Collaboratory, Jamboard, and so on. For me, it is showing Collaboratory here because I have already connected Collaboratory to my Google Drive. In case you have not connected, what you can do is you can just go and say connect more apps below. It is hidden here. Let me do. If I expand my so if you go to New, if you go to More, if Collab is not here, you just click on connect more apps. If you click on connect more apps, Google will show you what other apps that you can connect to your Google Drive. And these are some apps it is showing for me. You can search for Collab here. Do COLAB, it will show up here. You click on that, it will connect. So if you do that, you will have access to what is called as a Google Collaboratory Notebook. And if I do that here, it will start something like this. So in the simplest sense, it is basically a Python notebook, like a Jupyter notebook, a GUI for writing Python code. That is a basic Collaboratory. You can connect it. You click here on the right side, it will connect. And once it connects, you can go and write simple Python code. So an example here is this. I'm trying to type a is equal to 1 and press shift and enter. So what we need to do is press shift plus enter to execute. And each of this is a cell. So a is equal to 1, whatever tab you see like this is a cell. You can press shift plus enter to execute. You can also press on the play button here. If you press on the play button here also, cell will get executed. If I type A, in the next cell I type A. If I type A in the next cell and press shift enter, it will show me that A value is 1. You do this, B is equal to 2, shift enter, it will assign B value is 2. C is equal to A plus B, shift and enter, it will do the operation. And you do C, shift and enter, it will show you 3. A equal to 1, B is equal to 2, C is equal to 3 is the answer I am getting. This is a verification for us to know that Python code is running. Very simple. You can connect and then you can run. It is you being able to run Python code on the browser without requiring any hardware on your side. Now there are various options here. You can go and change the runtime. Runtime you can choose whether you run with no hardware accelerator, or if you are doing something intensive on GPU, you can use GPU. You can also use TPU. TPU is tensor processing unit. Only small catch here is you use GPU and TPU, your time will be restricted. They will make sure that you will only be able to run for some time and not all the time. So coming back to the notebook, we will just close this thing and we will go to our data set. Sorry, there is an interaction between these two comments. Yeah. So we will start with the exploratory analysis. Before we do anything, we need to do exploratory analysis. And one thing that we need to do is we need to be able to access data. I showed you a collab notes where you are simply doing A equal to 1, B equal to 2. But if there is a CSV file or a data set, how do we access? To do that, we need to use this command. You import collab from collab import drive and connect your Google Drive. Most of you may be familiar. What I am doing right now is connecting my Google Drive to my collab notebook. You may not be able to do if you are using my code. You have to copy this folder into your Google Drive and then only do this. So it will say, go to the URL on this browser, go there, click on the URL and give, this is my account I want to connect. And then go down and say allow. If you allow, it will give you a code. You just click on the clipboard. You copy the code, go back to your collab notebook and do Control V, paste it and enter. If you enter, your Google Drive is connected to your collab notebook. Basically, whatever files are there sitting in the Google Drive, you will be able to access from your collab notebook. And I'm setting my directory. Directory is where my data files are. If you go back to my Google folder, my data files are in my drive, collab notebooks, 2020 1215 SRM FDP1. This is the path where the data files, CSV files are. So if I need to go and access them, I need to set the directory. I'm setting the directory as content drive, my drive, collab notebook, 2020 1215 SRM FDP1. So that any file is there, I'm going to access the file and I not give the full path. So I set the directory. And as ma'am was mentioning, most of you have been introduced to pandas and numpy yesterday. So given any new folder, any new file, I want to access this file, AB_NYC_2019 CSV. I need to access that. I'm simply doing dir plus that file name. What is this? Why are we adding strings like we are adding numbers? In Python, strings are also like lists. It will simply add. So if you do ff is basically the directory that you saw here plus the file name. You add both of them, you are accessing this file, content my drive, collab, notebooks, SRM FDP1, ABC 2019 CSV. This is the file that I'm accessing. By only giving dir, I'm making it easy for me to access. I'm reading the CSV. So df contains the CSV file and the length of df is how many entries are there. There are 48,895 entries in the Kaggle data set for Airbnb. It has given us 48 or 49,000 observations. And before we go to do any analysis, we typically inspect one entry. One entry meaning what is a typical observation looking like. We inspect that. So if you do that df.iloc, iloc is a location entry. Okay, sorry, that doesn't. Okay. 1 minute. There seems to be a. Sorry, I went to the wrong sheet. Yeah, we inspect one entry. One entry is basically one of the rows in the data set. The row has these column names. There's an ID, name, host ID, host name, neighborhood group, latitude, longitude, room type, price, and so on. All these are there. And these are the values. So ID is a number, which is a unique key. Name is the description of the apartment. Host ID is the ID of the person who is hosting. Host name is Chris. This is in Manhattan. The neighborhood is Murray Hill. Latitude, longitude are given. What is the type of the room? Is it an entire apartment that is being given as on Airbnb, or is it one room in the big house? What is the price in dollars? If you want to stay there, how many dollars per night? And how many reviews did they have? And what is the, then was the, they had 74 reviews and they have a minimum nights constraint, which means the guest has to stay there for minimum 3 nights. You can't simply say 1 day and go. So this is the restriction that the host will place. When was the last review? June 22nd. How many reviews are there per month? Uncalculated host listing and availability. Availability 365 is simply throughout the year, how many days is the property available? And here it says that the property is available for 130 days, which is roughly like 4 months or 5 months. Rest of the time, the host may himself be using the house. Now we will go on to describe on the data. Describe on the data set will simply describe each of the column. Numerical columns only it will describe. ID is a numerical value if you see. So for ID, what will you see? You will see the minimum ID, which is 2539. It is just a scientific notation, but minimum ID is 2539. Maximum ID is a very large number. And then there is a range of ID values. Similarly, you have latitudes, longitudes, you have count of unique entries, and then you will see how many reviews are there and so on. If you look at number of reviews, the minimum value is 0. Maximum value, there is a property which has 629 reviews. And the other values are quantiles. 25 percentile quantile is 1 review, median is 5 reviews, 75% is 24 reviews, and so on. So this will help us just get a very quick idea of the data set. How is the data set looking like? And then we will go to print the columns. Any questions? I hear some sound. Somebody has a question? Okay. Then we go to print the columns. These are the column names again that we saw. And how many columns are there? It has 16 columns. And then like we saw in the earlier PPT, lot of them may have missing values. Any questions, madam? Okay, we'll go on then. Maybe somebody is not on this. Fine. So we will look at the columns and the missing values. How many columns have missing values, or what is the fill rate for all these columns? That is what we will try to figure out. So we will see what we are doing. This is a small code to print in each column how many unique values are there, how many missing values are there, and we will see that columns like last review, review per month, and all have lot of missing values. So if you want to build a model, you should be clear that we cannot build any model, or we cannot use review, last review, or reviews per month as a feature, because there are 10,000 missing entries there. You have 48K data set and 10K entries are missing. If you want to use last review or review per month in your model, you are very well sure that you have to throw away or discard 10K entries, because you cannot populate the 10K entries directly. And if you want to model something, the ideal modeling variables are the ones with least missing values. ID may be something, but ID is not really useful. It is just a unique identifier. But neighborhood group, neighborhood, latitude, longitude, room type, all these have no missing values. These are very good candidates for you to model. The model we are trying to do is to predict the price of the listing based on the properties, neighborhood group, latitude, longitude. Based on all those, we are trying to predict the price of the house. Now, before we even go to build a model, we can always try to build a model. But before we go to build a model, it is informative to do an exploratory analysis to see what does the data look like, and are there any features that I can understand by looking at it visually or inspecting the data, which are more important or which turn out to be interesting insights. So here, what we did was we simply did a scatter plot of longitude and latitude. Longitude is in the x-axis, latitude is in the y-axis. You do scatter plot of the properties, you see something like this, which means basically this is the plot of map of New York City, because it is surrounded by the sea. Properties described in these dots are basically on the map of New York City. Somebody is talking. Yeah, sorry, ma'am. So we can get some more information from this by doing this, by plotting the neighborhood group, which is basically given as a column in the data set. The neighborhood groups are this: Brooklyn, Manhattan, Queens, Staten Island, and Bronx. You give a hue based on neighborhood group. You know that these are the different groups in the data set. So in the New York City, there are 5 regions. One of it is Staten Island, the red one here. Blue is Brooklyn, orange is Manhattan, green is Queens, and then Bronx is the purple color. So these are the different neighborhood groups. So before we even go to any model, again we need to do some more analysis to see, are there any preferred regions? Where are the most properties located in? I see that this is how the map looks like. Let me see how many properties are there in each geographical area. So you see that Manhattan and Brooklyn have the highest number of properties listed on Airbnb. So you see this, Manhattan is here orange and Brooklyn is blue. These two have the largest number of properties, followed by Queens, Bronx, and so on. And then what are the types of rooms? Is there any specific room type to one geographical area? Are there more apartments in Manhattan, and are there less private rooms in Manhattan? We want to see. You do a scatter plot, you don't really see anything else. There is not much of a signal in this thing. When we look at what are the types of accommodation, we saw that there are 3 room types. So what are the types? This is a pie chart of distribution. We see that 52% or more than half of the property listings are entire homes or an apartment. If it is an apartment, full apartment is for the Airbnb guest. Or if it is a home, the full home is for the Airbnb guest in 52% of the listings. And 45% of the listings are private rooms. In a big house, there is a room that is private to you. And very minimal are basically shared rooms. Shared room is where you will share the bed with somebody else. Now this can be understood from the fact that this is New York and a business center. So most people traveling there may not be students. Maybe most of the time business travelers share the room.
For this inaugural session of 4th National Teachers Congress,
I
inspiring
hear,
teachers, strengthening generations.
sir, can you go on mute, sir? I see a camera and a fan.
Privilege to welcome each one of you to this very, very special session of the 4th edition of National Teachers Congress.
Balaji Patil, sir, can you go on mute?
वाचको दर्शकस्तथा शिक्षको बोधकश्च
Hello.
षडे गुरुभा स्मृता.
Balaji Patil, sir.
The one who motivates, the one who indicates, the one who tells the truth, the one who shows the path,
Ma'am, can you ask
the
sir
one
to go
who
on?
teaches, and the one who enlightens is the Guru.
Hello.
I
Golda,
welcome
ma'am.
all the teachers, mentors, educators gathered here
Golda, ma'am,
for
can you
the
hear?
inaugural session of
Hello.
4th National Teachers Conference.
Hello.
Before we begin,
Can you hear me, Golda, ma'am? Hello.
Yes, sir.
Yes, sir, we can hear you.
Okay. Yeah. Sorry for the trouble. I think some sir went on unmuted himself.
Yes,
Okay.
sir. No.
Yeah. Fine. So this is the type of accommodation. Primarily, this because this is a business destination. Now, if you did the same Airbnb analysis for somewhere near a college, say somewhere in the middle of US and all, you might be seeing more of shared accommodations than accommodations like this. Then we go on to another thing on the room type and see how many counts are there. There are 25K apartments, 22K rooms, and then shared rooms are 11,600. And then we will also see what are the types. It's just a different representation of the same thing. And the next one is how are the prices distributed. Price is what we are going to predict. So let us describe the price and see. We describe the price and see. Some of them had a price of 0, which is basically false or wrong data. Nobody would be saying my apartment is rented out for free to you. So 0 is a bad data or an outlier. 25% value is $69. The maximum value is $10,000. So if it is anything to do with the number of days, even $10,000 per day is a bad number. $0 per day is also a bad number. So we need to take care of removing these when we go on to do any modeling. So to do that, we do quantiles. We are already seeing 3 quantiles here, 25, 50, 75. But we go to a more detailed quantiles, which would be 1 percentile, 5 percentile, 10 percentile, 90, 95, and 99 percentile, which is what you see here. So we can choose various metrics. You can choose to cut off from 1% to 99%, or you can also choose to cut off from 5% to 95%. So if we filter data from 5 percentile to 95 percentile, we see that $40 and $355 are the probable numbers. So we filter the data set by that and look at the prices. We see an interesting trend. Can anybody spot the interesting trend that you see? The histogram x-axis is the prices and the y-axis is the number of observations. That is what we are seeing in the histogram. And you see that there are peaks. There are peaks where there is a rounding off that is happening. At $100, there are a lot of properties. $150, there are more properties than $140 or $160. At $200 also, you see a similar trend. This is human behavior, right? We tend to round off. You don't really ask for $149 or $163 per night. You will either ask $150 or say $175. So that rounding off is what you are seeing here. The peaks are basically numbers: $75, $50, $100, $150, $200, and so on. There are a lot of properties listed at $300 than at $290. Then we will just go and explore something more about the host. What do we know about the host? We are grouping by host ID and doing a count. We see that there is a host whose ID is 219517861. This host has so many properties. The group by is on the properties. The group by is on the host ID and the count is of the properties. We see that there is a host with 327 properties. So is this an individual host or is this somebody else? We will see. How do we do or what do we do? We just go and describe, and we will see that there are a lot of hosts. We look at the percentage of hosts with at least 1 property, at least 2 properties, and so on. This is a distribution primarily because we see different numbers here. The maximum host has 327, but most of them seem to have 90, 95, 100, 49, 30. Most of them seem to have more than 1 property. So we will see how many such people are there. So this cell is simply a summary. At least 1 property, all the hosts have at least 1 property, which is common sense. If they don't have a property, they will not be here. But if you look at hosts who have 2 or more properties, at least 2 meaning 2 or more properties, then 13% hosts have at least 2 properties. They can be 5, 10 or more. At least 3 properties is 4.87% hosts. At least 5 properties is 1% host, and at least 10 properties is a minute fraction. 0.31% of the hosts. It is not 0.31 fraction, but 0.31% of the hosts have more than 10 properties. So basically, hosts with more than 2 properties are small or a minimal number, not a big deal. but then they indicate some interesting phenomena. So what do you see here? We will see max host ID. I'm only going and picking up the host with the maximum number of properties and seeing what they have. This is just a summary of the big host. Now, if you look at this, this is the name of the property of that particular host. Host ID is same and properties IDs are different. For that host, I'm picking up all the property IDs. What do you see? The name is Sonder 180 Water Incredible 2BR Rooftop. Sonder 180 Water Premier 1BR Rooftop. So there is something common, Sonder. So you go and look at the host name. It says Sonder NYC. If you go on Google, you will see that Sonder NYC is a hotel. So basically, it is not an individual host. It is a hotel which has given their neighborhood apartments on rental. This is a big company which is giving their properties on rental. It is not one individual person. So a company is coming and giving out their apartment. So this is like a hotel or a chain of rooms which is letting out apartments on rent, which is also being added in the Airbnb dataset. That is what we see. So we need to be cautious about how the pricings are, because the pricing for an individual host may be different from the pricing from a big host. So you look at the big host prices. This company Sonder has properties ranging from $100 per night to $700 per night. They have various kinds of properties. That is what they have. And then there are few more questions you can go on to explore. I will leave them here in the interest of time. There is a question on how many nights do they want to stay, availability, all other things are there, and what factors are affecting the price. All this you are free to work out on your own. Because we have come to nearly to the end of the session, I want to go to the modeling part. So let us go to the modeling sheet. The modeling sheet is basically a new sheet which will just do the model. I need to repeat the process of linking my Gmail account to the modeling sheet. So it is connected, and then this is all the preliminary analysis that we saw anyway. So I'll skip them in the interest of time. It will simply print length of DF is 48895. This we saw already. So we'll skip all this and we will directly go to the modeling part. All this is, most of it is already known. So we look at the quantiles. We also saw this, and then we will do, before we go to model, we did the EDA, and we can also do some more analysis on what factors affect the price. And how do we know what factors affect the price? We need to do this. We need to remove the outliers and then look at each of this column to see whether each of them has an effect on the price or not. So if you look at room type, like sir has asked earlier, this is a box plot of different room types and their prices. So you see that entire home or apartment has a high median value compared to private room and compared to a shared room. Shared room, private room, there doesn't seem to be much of a difference. So the middle line is the median, 25% is the lower line, 75% is the upper line, and this is the interquartile range. So you see that the room type has an effect on price, much like the time of the day having an effect on our Uber trip. So we need to bring in the room type into the regression model. So one thing I did not mention in the PPT is that handling categorical variables. So here, home type as a room or an apartment or a private room is a categorical variable. It is not a number. So how do we handle categorical variables? Whether the accommodation is apartment or whether the accommodation is private room. How do we handle that? We handle them by what is called as one-hot encoded flags. So what we will do is we will do one-hot encoding, and using the one-hot encoding we will try to predict. So we will give a flag: room type apartment 0 or 1, private room 0 or 1, shared room 0 or 1. We will do categorical flags and use those flags as a regression model. So room type has an effect on price. Neighborhood group has an effect on price. If you go and look at this, the neighborhood group itself has an effect on the price. Manhattan is high price than Bronx, Brooklyn, Queens, Staten Island, and so on. Then you see the mean values for Manhattan is $151 per night compared to Bronx or compared to Staten Island. And does minimum nights have any effect on the price? We are seeing, because they say host say 1 night minimum, this is the price. 2 nights minimum is slightly higher price, and so on. There is lot of variation, no big signal, but we can still try to model it and see if there is any interesting feature that will come out. So I just converted the minimum nights to weeks. You see that 1 week, 2 week, or 4 week are similar prices, but 3 weeks is a lesser price. Similarly, 6 weeks is a lesser price compared to other properties. And number of reviews, does it have any effect? Or calculated host listing, does it have any effect? All these we can see. And then one interesting thing to note is that some of the apartments have zero availability. They say the availability is zero. So when we go to model, do we need to consider the availability flag or not? If the property is not at all available, do I still need to predict a price or not? That is a question that we can answer by looking at the data. What I am doing here is splitting the data set into two parts. One part is all the properties which have zero availability, and one part is all the properties which have non-zero availability. So DFC0 is all properties with no availability or availability of 0 days. DFC1 is all the properties whose availability is greater than 0 days. And then look at the histograms of the prices. You see that between 0 and 1, there is not much of a difference in prices. So there is no need to exclude properties which have zero availability. That is the conclusion. Whether it is zero availability or whether it is 120 days of availability, prices do not change. So let it be there in the data so that my model has access to more data points. That's all we can conclude. We can keep them in the data set. So these are some other flags like that, full availability or not, or something like that. You can explore these things as well. We will look at minimum nights constraint also. Minimum nights also has different values. You see the maximum, somebody said the maximum value of minimum nights is 1250 days, which is 4 years, which means the host is saying you have to stay for 4 years in my property. That itself is a false value or a wrong value. We cannot let it be there in the model. So we do quantiles on the minimum nights. You see that minimum nights are starting at 1, and the maximum or 99% value is 40 nights. 40 nights will roughly turn out to be somewhere around 6 weeks or so. Then we will go to build a simple model. We will not try complicated model first. We will try to build a simple model. To do a simple model, there is something that we need to do. We need to read the training and the testing data. Okay. So before we even go to anywhere else, I wrote a set of functions to train the model. I will just walk through the functions one by one, and then we will go to the model. So from sklearn, I'm importing the linear model. Linear model is a linear regression that we saw in the talk. Then these are the metrics. R2 score is the R square error that we are referring to. Mean square error is the RMSE error that we are referring to. And then we are also doing train and test split. If I want to split the data on my own, I will do train and test split. These are the input. These are the packages that I'm downloading or loading into Python code. Then there is a clean data function. Given any data frame, it will clean based on 95th percentile and 5th percentile of price, and then return the clean value. This is one function. The other function is convert to categorical variable, meaning if I have apartment type to be what do you call full apartment or shared room, how do I include that in the model? We have to do it as a categorical flag. This function will do that as a categorical flag. So let us run all these functions and go down. This will convert to categorical. This function will return the metrics. Y true minus Y predicted, it will return the R2 score and it will return the mean absolute value of error. And then I am going to do the modeling on the trained data. So please observe the data set is there. We did the EDA on the entire data set. But I have also split the data into two parts, train and test. So 6 MB file is the training data and 1 MB file is the testing data. So we are going to build our model on the training data. I am not building it on the test data. Train data is 39K observations, 39,000 observations. This is how the train data looks like. I will clean the train data. By cleaning, I mean we are removing the, if you go back and look at the clean function, we are simply removing the outlier prices. So if I remove the outlier prices in my train data, 39,000 observations become 35,000 observations. And then these are the columns in my training data. Now what we are trying to do is this. We are trying to convert to categorical two columns, room type and neighborhood group. And these are the only two columns I will use in the training data set. So let us look at this. So this convert to categorical is a flag that I gave, and it is converting the df train into a new data frame, which is df train 2. It will have categorical flags. So these are the features for the df train 2. df train 2 has minimum nights, price, number of reviews, and so on, and it also has categorical flags. How do the categorical flags look like? We have the description here. Now if you see, the room type has now become feature, entire home or apartment. So to bring out the difference, I will just print one small thing, which is df train.head. So if you look at df train.head, what you will see is this. The room type is a private room or an entire room or a entire home or apartment and so on. This is what we see as a room type that we have converted into a categorical feature here saying entire home or apartment 0 or 1, private room 0 or 1, shared room 0 or 1. So if the accommodation type is a private room, only that will be 1, the other 2 will go to 0. And actually you can drop one of them. If there are only 3 types, you can drop one of them. That also we will see. And then we will train a simple linear regression model. And you train a linear regression model, it will give 2 values. One is the R square value 0.42 and the other is the MAP value which is 0.35. That there is a 35% error in prediction and our R square is 42, 0.42. It is not close to 1, meaning we have not got a very good model as such. But this is still on the training data. Now let me see how is my performance on the testing data. Testing data is unseen data and there are 9,600 entries in the testing data set. If I do the cleaning, it becomes 8,800 entries. And I do the same process. I convert room type and neighborhood group to categorical. Same things that I'm doing on the training data and then doing predict. So predict will simply give me the trained model. The input entries to predict are the D of test2, which is the testing data set. F1 is basically the set of features that we are using, and the model 1, which is the trained model. Model 1 is what we trained here. When we are training, when we say, let me just show that here. Yeah. When we say linear model, linear regression and train model, in train model, df train2 is sent in, list of features are sent in, and model 1, which is a linear regression model, is sent in. And what is returned is a trained model. There is a model dot fit inside, and the trained model, there is a model dot fit inside, and it will return a trained model. So you take this trained model and go on to predict on the test set. That is what I am doing here. So we can try another model if you want to. If from here you can go on to do multiple things. What you saw so far is a base model has 0.42 as an R square or 0.41 as an R square on the regression value, and the model maps are bad. One has 0.35 test map and the train map is also 0.35, which means that our model is not doing extraordinarily bad. The model is also not doing extraordinarily well. From here we can try to improve the model. There are various things you can do to improve the model. You can try to improve the model by adding more features, going to something like a random forest regressor or going to something like that, and then you can try. So the model here has another thing called random forest. We can try out random forest regressor and see. We can also try out XGBoost regressor and see. And one thing that people observe is that the prices are not normal. If you look at a histogram of the prices in the EDA file, you see that they are not normal. So we can do a log transformation on the prices. So this is called a feature engineering, feature transformation on the data set. So if you come back to our original data set and if you look at the prices, you see that this is not a normal distribution. This is basically a distribution that doesn't look normal. By normal we mean it doesn't look like a Gaussian distribution. So what we do, we can do a transformation of log. So if I do this, sorry. We will see a distribution that would come out of a logarithmic after doing the log transformation on the price. What I have done is I have excluded the outliers and then did a log. Instead of plotting P, I am plotting log of price. That looks more or less like a normal distribution. So people also tend to build models where the prediction is of the log of price and not the true price. Instead of predicting the true price, we will try to predict the log of price. This also can improve the model performance. So these are some 3 or 4 things that you can do. Very short time to learn in detail, but I have tried to cover as much as possible, and I am willing to take any questions. Thank you for listening to me patiently. These data sets and notebooks are there with you. Please feel free to explore, make a copy, and then you can go on to build your own model. Thank you very much. Any questions? I'm willing to answer. Or please feel free to ask me any questions that you may have.
Participants, in case you have any questions, kindly ask.
So maybe go on. Sorry. So maybe just a sense check. Is everybody familiar with Google Collaborate running codes online? Or in case if you are not familiar, you can also install Python locally and then run your own codes locally. So there is something called Jupyter Lab. If you are using Windows, there is something called as Anaconda. Anaconda is a Windows package which will help you install all Python and all kinds of things locally. So you will have, you just go and follow what they give as an Anaconda distribution. You can install Python, all packages in Python. This works with Ubuntu, this works with Windows, whatever you want. You can install Python in your local machine and try out all these codes also. There is no restriction. You can do it locally. You can also do it online. The easiest way to experience is online via Google Collaborative, which works with your Google Gmail account. Any questions or any thoughts? So please feel free to ask me anything else also. It may not be related to regression, but anything else about machine learning also, I'll be more than happy to answer.
Yes, participants, any queries that you have, kindly feel free to ask.
So thank you so much, sir, for your insights. I really appreciate you taking the time to share these very useful resources. It was very excellent session, sir. Thank you so much. Dear participants, the feedback link will be shared in the chat box and it will be open for only 15 minutes from now on. And so there is an appreciation certificate for you and we'll be sharing that with you, sir. Thank you so much, sir.
Yeah, thank you very much, ma'am. Thank you very much. I'll share an updated PPT. There are 1 or 2 typos. I'll share an updated PPT. You can share it with the participants.
Yes, sir. Sure, sir. Thank you.
Thank you, ma'am. Yeah, Meenakshi, ma'am. Thank you very much. See you.
Thank you, sir.
Thank you, ma'am.
Small token of appreciation from our end, Dr. Vallabha. Thank you so much for the wonderful session. I'm sure the participants are going back with a lot of takeaways from this session. Thank you so much. Thank you. And we look forward to seeing you on the final day for the reinforcement learning session as well. Thank you so much, sir.
Sure, ma'am. Yeah, thank you very much.
Dear participants, today we'll be having a special session on AI skill enabling the path forward by Mr. Unnikrishnan sir. So we request all the participants to kindly join back by 1 p.m. itself. So kindly note the time, it is 1 p.m. and it will be continuing until 2 p.m. And after that, we'll be having the another session. So please, the participants kindly join back by 1 o'clock. Yeah, the feedback link is shared in the chat box and we request all the participants to give your feedback. This link will be open only for 15 minutes. Thank you all. The feedback link has been shared. So please take your time to share the feedback and this will be maintained for attendance also. So once you have submitted the feedback, the participants can leave the meet. Thank you.